everyone, and welcome to our session. And it's 3D UI Gaze number 2. We run each talk followed by a short Q&A. And if I need us on the schedule, I give a gentle signal, of course, but I believe it will be not necessary. So for one presentation, should be take around 15 minutes together with the Q&A. So across this hour, we look at how gaze and viewpoint share interaction. So let's start with the first presentation. Stage is yours. Thank you.
Thank you very much. Hi, my name is Daniel Delgado. I come from the University of Florida, and today we're going to be presenting when is self-gaze helpful? Examining uni versus bidirectional gaze, visualization, and collocated AR tasks. And this work was done with my partners, Christopher, Rodrigo, and Jamie. So what exactly are shared gaze visualizations? Shared gaze visualizations, or SGVs, are a way of presenting mutual understanding and eye-tracking information in augmented reality. It allows collaborators to understand each other's intention and attention while working together on tasks. And they can be implemented in a variety of ways. On the left, we have a gaze ray, which presents a laser that comes out of the headset. We additionally have ways of presenting additional information like gaze history, or for example, how your eye trails throughout information, as we see in the middle. And there are also ways of presenting gaze visualizations through methods that are disconnected or detached from the user itself by highlighting an object as seen on the right. Now, while beneficial for performing different tasks and providing mutual understanding, shared gaze visualizations present a variety of limitations. For example, they have a distractive nature. For example, they get in the way. Additionally, dynamic-based visualizations, as we can see on the top left, can be confusing with users not understanding how the visualization changes over time based on things like gaze dwelling, intent, and focus. And for the most part, gaze visualizations have not been studied in an applied task, mostly in abstract scenarios that are static and don't really utilize the full potential of the gaze visualizations. And overall, there seems to be a common theme through all the implementations that have been provided from prior work, in that they tend to be distracting. And it mainly tends to be a problem with users' own self-gaze visualization. And it begs the question, why does the user have to have an actual gaze visualization presented in front of their face at all times, always following their every eye movement? People, for the most part, don't want to have that, and it doesn't seem necessary because I know what I'm looking at, so why is that visualized? So understanding these limitations, I was curious to understand where the motivation to always present the self-gaze came from, and it actually comes from remote applications where it is necessary to have feedback to determine that the visualization is currently tied to what I'm currently looking at. So for example, in real life, if I'm talking to you and I'm looking the opposite direction, it's easy to tell that the visualization is not where it's supposed to be. But in an application where the two people are separated, like a Zoom meeting, for example, it is necessary to have the feedback to determine if that's currently correct. So with this in mind, I redeveloped the research questions: how does self-gaze affect user perception of shared gaze visualizations in augmented reality? And additionally, what are the benefits and detriments of visualizing self-gaze in a collocated task? And does the type of visualization, for example, like a gaze ray, gaze hover, highlighting the object itself, affect a user's perception of self-gaze? So with this in mind, I developed a methodology of a within-subject study of a 2x2 of visualization by directionality. Directionality meaning I present the visualization of my partner and myself, and the type of visualization being ray and hover, which I'll present in a couple seconds. So with a medium effect size study, I ended up recruiting 21 participants in a paired study, meaning that participants took in a task with a partner. The reason why it is an odd number, not an even number, was that we used confederates during the research study, and we used specifically 3 to help participants take part in the task without having to always have a partner, but their data was not used in the data collection. And we collected participants ranging from 18 to 41 years old. So as we can see here, we have the first example of uni and bidirectional using the ray visualization. So on the left one, we have the bidirectional, meaning that my partner's visualization and mine are both seen. And you can kind of see based on the two red lines that extend from the headset. And on the right one, we only have, of course, our partners. And this is, of course, the ray visualization. The next one that we have for determining the uni versus bidirectional is the gaze hover. And gaze hover highlights the object. So on the left, you can see the hot dog of myself is highlighted, but on the right, it isn't. The one for the partner is a little hard to see, but it is the toilet paper that is highlighted. And I'll explain the task in a second and why these objects are presented in the screen at the moment. So in order to elicit eye-gaze interactions in a dynamic task environment, we wanted to evaluate the visualizations in a setting in which the collaborator would rely on the visualizations for communication while also justifying the use of augmented reality headsets in practice. So we simulated a recycling plant conveyor belt sorting task in which users were in a scenario in which they were instructed to use augmented reality headsets to help them sort through dangerous recycling material. As you can see here, workers have to work together, communicate with each other while also working in a hectic environment, and signal to each other while also using their focus. So there's a lot of things going on that also help shared visualizations be utilized to its full potential, as well as using augmented reality to identify dangerous objects and justify its use in practice. So the study set up for this exact scenario was we had a physical desk within the room, as well as 4 cardboard bins that simulate the different materials that users had to sort in place. And for the task, users had plastic, paper, metal, and glass that they had to pick up, as well as trash that they had to ignore. Along with, within the trash itself, there was objects that they had to kind of avoid touching at all, which were highlighted red based on the augmented reality headsets. So as we can see here, objects would flow down this virtual conveyor belt that was placed on a physical desk itself and then pick up the objects and place it in the bins itself. And they stood in front of each other while working through the tasks. That way they could elicit the eye-gaze interactions that we were looking for. And on the next task, I'll present the space itself. So as you can see here, we have a physical desk and the virtual objects are flowing down. This is my partner, and of course, as you can see, this is the bidirectional visualization because both my ray and my partner's ray is visualized. And you can also see the 4 cardboard boxes in which the objects are placed within the task itself. So understanding this, we developed some data collection metrics for the task itself, in which we collected the number of objects sorted, the number of dangerous objects touched, and for qualitative, we collected a collaborative feedback survey, which provided us with participants' intentions, focus, attention, reaction, and interaction throughout the task while they were engaging with the different visualizations themselves. And finally, we collected a visualization comparison and feedback survey at the end of the whole study. So there was 4 conditions in total, so it was within subjects, and we collected the collaborative survey after each condition itself and the final visualization comparison survey at the end of the whole study. So with our results, we conducted an align, rank, transform, and ANOVA on the data itself because we wanted to see the individual conditions as well as the combined effects of both. For the most part, what we saw from the visualization preference was that participants significantly preferred ray over hover, which was not surprising because the hover visualization did tend to occlude the color of the objects as well as make it difficult to tell whose visualization was whose. So seeing a bunch of things being highlighted on a dynamic conveyor belt was very confusing. And yeah, when looking at uni versus bidirectional, however, we did not see any significant difference in participant preference, but open responses did get to highlight what was unexpected, which was that although the unidirectional condition helped participants feel like it reduced distraction, participants felt like they were not a part of the task. And this can be explained by the fact that participants would be working together with their partner, but they only saw their partner's visualization. So they would be standing there working with them, but they only saw their partner working based on all of the virtual information that was presented in front of them, which was kind of interesting. And overall, the combined interaction effects of directionality and the visualization did not produce any significant effects. So some key insights that we were able to gather from the study itself was overall, ray was less confusing, with participants saying, it lets me see what he is seeing without overloading my view. In a dynamic environment in which shared gaze visualizations are implemented to provide mutual understanding of collaborators, it is kind of overwhelming to have so many moving parts, which is understandable. Again, as repeating as before, it was kind of unexpected to see that the lack of visualization reduced confidence within partners, with them saying, I did not like that it was not highlighted. It made me feel like I was doing nothing at all, kind of giving this psychological effect of participants feeling like they weren't a part of the study itself because only their partner's visualization was presented in the task. And finally, participants did comment on reducing distraction with only being in a unidirectional setting, saying that it was very effective at showing where my partner was looking without the distraction of my own focus. And to conclude, we evaluated a study of uni versus bidirectional tasks through a dynamic industrial task. Unidirectional may reduce distraction, however, also may reduce confidence and presence within the task. For the most part, there was no significant effect of visualization on self-gaze. And some overall recommendations that we make with the future development of shared gaze visualizations is communicating the ownership of visualization, specifically where the visualization is detached, like for the hover example, in which participants kind of see objects light up and they can't directly associate who's looking at what based on that. And finally, preserving natural interactions, as we saw how visualizations can influence the social presence of participants and themselves. So thank you. Do you guys have any questions?
So thank you for a presentation. Questions?
Yeah.
Thanks for the great presentation. You mentioned the ray being preferred over the hover. In the pictures that you showed of the hover, it was recoloring or highlighting the whole object. Do you think how much of that preference was because of the visual design? If it was like just the more subtle outline of the object, would that affect the results?
That is a good point. So based on the participants' comments, and also I'm kind of cheating because I have, there's another study that I did after this. A big portion of it was the design of the visualization itself. That could be attributed with the way the objects were highlighted and made it difficult for them to perceive what it was in the first place. So I do think it was a lot to do with the visualization design itself.
Any other questions? So maybe I have one. In busy scene, would you stick to one-way gaze cues?
Excuse me, I couldn't hear, I'm sorry.
In the base scene, would you stick to one-way gaze cues?
Are you asking if I would prefer unidirectional or bidirectional?
Oh, it doesn't matter.
I'm sorry, I cannot. Could you rephrase the question? I'm sorry. I didn't.
Oh, we can talk after the session.
No, 100%,
okay.
yeah.
Oh, we are on the time, so we can move to
No worries. Thank you so much for listening, everyone.
Yeah.
Let's start it. Hello, everyone. This is Zheng Wei. I'm from the Hong Kong University of Science and Technology. Today, I will share our study how gender, avatar, and narrative design shapes creativity learning in film education. This work looks at how students see and shout a story differently when they play as a role about the male or the female avatar in VR. Okay, first, our study explores the potential of the VR in film education, particularly in the learning film lighting technologies. So first, VR provides students with an immersive learning experience, breaking the limitation of the traditional physical classroom, right? Allow them to practice repeatedly in virtual environment and similar to various film scenarios. However, despite the widespread use of the VR in education, there has been limited research on how different virtual environments influence student learning, especially in creative fields like the film production. So we ask for the question, how do participants and avatar gender affect persons and self-persons? And the second is, how do narrative gender and the embodiment influence creativity choice like shoot and lighting? And third is, how do these factors shape the understanding of the male gaze and the female gaze. And how do these interactions influence the overall learning experience? So this, we hope to understanding how gender dynamic changes what people see and creative in VR. Before this study, we knew the background about this study concept. There are three key ideas. First is self-presence and avatar consistency. When your avatar looks like you feel more immersive. When it's different, it means sparks creativity. Second is spectral effect. People often behave like their avatar. For example, acting more confident, or the gender depend on avatar feature. Third is male and versus female gaze. As we can see, the figure is simple. The male gaze often shows the action, contract, and the body. And the female gaze focus on the emotion, closeness, and soft light. So this concept guiding us all the experiments. So before that, we built the VR system called the Film Dance Studio. It simulates the real film production, camera movement, lighting, and actor direction. User can choose between the male or the female avatar and between the male lead or the female lead narrative. The studio includes the LED light, RGB color control, and large mirrors so your user can see themselves. So it's like a small film set inside VR where every student become both director and cinematographer. So here is also experimental design. We use the 2 multiply 2 multiply 2 factor design. User gender is male or the female, and the avatar gender is male or female, and narrative gender is male lead or the female lead. That gave 8 combinations in total. So for the user study, we recruit the 48 participants, half the male and half the female. Each had to shoot a 45-second dance sense inspired by a very famous film in the Black Swan under their assigned condition. So their final clip were rated by 2 experts. Both 2 experts had more than 10 years industry background. One is cinematographer, another is director. For the gaze style, is a male or female or the natural. So here is all the experimental pipeline. And we can see the figure 2 and figure 1 is the male user to use the female avatar. And the figure 3, figure 4 is the female user use the male avatar to do the short task. And let's see the demo.
Film Dance Studio is an immersive film production teaching system based on virtual reality technology. Integrating presence theory and the Proteus effect, it simulates a realistic filmmaking environment, enabling students to practice hands-on in virtual space and gain a deep understanding of complex lighting setups and visual storytelling techniques. Users can choose virtual avatars of different genders and complete a 45-second filmmaking task under either male-led or female-led narrative conditions. Through interaction with 2 virtual actors, users not only learn how to arrange lighting and operate the camera, but also experience the contrasting dynamics of the female gaze and male gaze in the creative process. In the training scene, users learn to operate lighting equipment and a virtual camera, familiarize themselves with their avatars, and observe their own movements in real time using full-length mirrors that span floor to ceiling. In the formal creation scene, the system encourages users to explore freely and produce a narrative-driven short film. The system supports various lighting fixtures and advanced lighting control, offering full adjustment of color, angle, and intensity. With a virtual control panel and interactive buttons, users can move and rotate objects, combining camera and lighting arrangements to take full creative control. Research on this system reveals that team collaboration in structured environments enhances efficiency, while individual learners show stronger creative expression in more challenging settings. Furthermore, when using avatars of a different gender than their own, users report a greater sense of control and immersion, leading to more reflective and intentional creative choices. Film Dance Studio is not just a teaching tool, it is a virtual platform that breaks gender boundaries and sparks creative expression. It reveals a new vision of film education, one that is being redefined in the world of virtual reality.
Okay, so here is all the result. First, we found a clearly interaction effort between the user gender, avatar gender, and narrative. Participants use an opposite gender avatar report higher presence and body awareness. They watched their virtual body more carefully and paid closer attention to forming. And gender-matched users often repeat the traditional gaze style. Like the male user with the male avatar, they often choose the high control action focus on the shoot, that means the male gaze. And for the female user with the female avatars, you also use the soft light emotion focus, that means the female gaze. Both cross-gender users often switch style. They use the opposite gaze, creating more balance. So a gender mismatch accurate encourage reflection and creativity. And here is all the detail. As we can see, the red benchmark is more significant based on the iGroup percent questionnaire and the user experience questionnaire. And okay, here is all the expert result. Each participant shot a 45-second dance-inspired black swan. They controlled light, camera, and angles. Experts judged whether the shot shows the male or the female gaze. We observed that the male-female sweep often changed camera behavior. For example, a male user with a female avatar used a close-up and soft light. A female user with a male avatar performed a wider dynamic shot. They confirmed that embodiment shaped storytelling. And for the post-study interview, user with the same gender avatar offside, I don't really notice my avatar. User cross-gender avatar, they can say it's flat different from the real life. I watch myself more. They also notice gender power change in the dance. Some said the female dancer is leading, that Philip knew, and the other said I try to balance both the dancer in the film. So this reflection shows that VR teach the emphasis and the perspective awareness, not only the camera skill. Now that is all the limitation. For the limitation, we had only 48 students from one university, so the generation is limited. And next is we only focus on the male and female avatar, which means the real world diversity. And we realize the self-report skill, which can be biased. Next, for the future work, first we will do the recruit larger, more diverse group, and we will study team filmmaking in VR and test other cues like the body, face, and voice to see how they shape the creativity choice. So here is the conclusion. First is cross-gender embodiment challenge visual habit and the building emphasis. VR film training can teach both technique and the gender perspective. Avatar and narrative gender inspired can serve as a teaching tool. Our design recommendation is we can to offer flexible avatar and narrative options. So students can explore the different gaze and learn more inclusive storytelling. Thank you for your listening. This is the work shows that VR is not only a camera tool, but also a mirror of the perspective. By letting learners switch the roles and gaze, we can help them see film and themselves in the new ways. Thank you. So the final slide is my co-author, Professor Xu, recruits a PhD student at Lingnan University with a full scholar focused on the art technology, data storytelling, and VR education under the, yes, you can contact her via email. Thank you.
Thank you very much. Any questions, please? No questions. All right. I saw you mentioned we can use as pedagogic for teaching as a tool. I would like to use that in the teaching.
Oh yeah, I think it's a good question. So my study is focused on the film industry virtual reality system, and just for now, we have more than 6 different systems for the film long-term training, and we also have the long-term training 2 years in the HKUST Guangzhou and HKUST campus. But for the long-term training, we found that virtual reality not just need to focus on the enhanced student technique, right? They also to enhance their perspective, the gaze, the understanding, what's the storytelling. Because for the future work, I think for the film or for the academic, storytelling is a very important skill. But students, they not only to study the technology, they need to pay more attention how to tell a good story, right? So that is the idea we want to students know what's the different, when you use a different avatar, different gender, yes.
All right, thank you very much.
Okay, thank you.
So, hello everyone, my name is Clara Seifert, and in behalf of my amazing co-authors Annika Köhler, Julian Rasch, Albrecht Schmidt and Florian Müller from LMU Munich and TU Darmstadt, I'm going to present our work today through the expert's eyes, exploring asynchronous experts' perspectives and gaze visualizations in XR. So let's start. Since we are young, we are learning practical skills through imitation from others. This is a very social process that involves a lot of social connection, and it can be especially helpful during complicated tasks where you need, for example, both hands. But what happens if this expert is not available? And this is a large problem in many countries, especially Germany, for example, where more people leaving than joining the workforce, and we face a teacher shortage in the future. So introducing multiple people simultaneously is not as effective. So we need asynchronous solutions. These, for example, could be simple video tutorials, but these lack spatial guidance, anchoring, and can also miss social factors due to their very focused view. Extended reality, on the other side, can visualize this expertise and social cues, and can be time independent. It can, in combination with AI, be tailored and also contextually anchored to where the information is needed. And according to related work, it also performs better in traditional video tutorial than traditional video tutorials in this task setting. Another problem is that in 2D videos we have this fixed perspective, so we know exactly where to look at, but with extended reality, this perspective is not fixed, which is kind of nice because we can change our perspective, we can see things from different viewpoints, but also we don't know where to look at, probably. So when we change our perspective to the first-person perspective for videos and synchronous extended reality, the performance can improve, and also the embodiment and social connectedness according to related work, but we also lose social cues like gaze as we change our perspective, so we don't see the head anymore, so we don't see where the expert is looking at. And this is a problem because there's related work out there that says that performance improves and also social connectedness when we use gaze cues compared to no gaze cues. But we don't know how this applies to manual asynchronous extended reality instructions, especially augmented reality instructions. And this led to our research questions. So how does the perspective, the gaze, and also the interaction effect of both affect the efficiency, embodiment, and social connectedness during asynchronous instructions of two-handed manual tasks? And in this talk, we only will talk about the first ones because due to time restrictions, but if you want to know more about this, you can read our paper. And so our dependent variables were the first-person perspective, as you can see here, and also the third-person perspective, where you stand it beside the instructor, and also we added no gaze cues, eye gaze cues, or head gaze cues, depending on the condition. This led to a 2x3 study design in a controlled user study setting, and it was a within subject design. We had a sample size of 36 participants and did an analysis on all the data, and our dependent variables, as already mentioned, were the perspective, the first-person perspective, and the third-person perspective, and also the gaze with non-eye and head gaze cues. And we not only evaluated everything like quantitatively, but also qualitatively to get like a feeling for the emotions of the participants. And we evaluated the quantitative data using the interface. I will give a little bit more information on that later. And also through videos, and we also did evaluated it through questionnaires, and we did also qualitative measures through interviews and qualitative notes. And for the task, we decided on a two-handed manual task that was shown to be avatars were shown to be very effective for these kind of tasks and related work, and this was also a very good use case to evaluate the gaze cues. In order to measure all of this quantitatively, we implemented a machine interface that was connected to a microcontroller and mirrored in the middle so that both hands could reach everything equally. Some of the elements were in the middle so that they also were better reachable because like the interaction was a little bit more complicated. And this led to like 8 different elements that were measured through this microcontroller. And here you can see like the first person's perspective. We chose only showing the hands in the first person perspective, and based on also related work what other people did. And in the third person perspective, a full body avatar as it was more realistic. For the visualization, we chose a realistic avatar to evaluate the social connectedness towards this visualization. And in the first person perspective, the participant stand on the position, so because the participant was in the view of the expert, and after the animation ended, the participant had to redo the instructions. In the third person perspective, the participant stand beside the instructor, watch the instructions, and then move to the position of the instructor, like it would be also in normal instruction scenario with a real expert on site. For the eye and head gaze cues, we based them on related work, and we chose like a donut visualization to also make them comparable against each other. Here you can see the third person perspective and the first person perspective in action. And also the eye gaze cues, you see they are very unsteady, and also the head gaze cues. And after that, the participants repeated the task. For our results, we had also more results, but I will just talk about the most important ones. When we look at the perspective, the performance increased for the accuracy, for example, in the first person perspective compared to the third person perspective, and also the time was overall shorter in the first person perspective than the third person perspective. When we look at embodiment, the embodiment increased in the first person perspective and decreased in the third person perspective, and the social connectedness also increased in the first person perspective compared to the third person perspective. When we look at gaze, the patients, so we also looked if participants started earlier with the task, so before the animation ended, and this increased when the participants saw eye gaze cues. This was probably due to the very unsteady visualization, so they probably got nervous themselves when they saw that, compared to the head gaze cues. And also, when we look at the raw nasal tail X, the non-gaze cues led to less mental demand than the head gaze cues, which could be as the head gaze was very far away from the actual happening. So the participants had to switch a little bit more with their eyes, and that led probably to the higher demand. Also, the participants stated, when we look at the usage, that they would use the non-gaze cues more often than the head gaze cues. And here are our key findings summed up. So first, the first-person perspective improved efficiency, embodiment, social connectedness, with some participants finding it unnatural or even scary. So some participants mentioned that when they were in the first-person perspective, because they also saw, of course, the third-person perspective, that the instructor was kind of behind them, and it felt very weird for them that they were in this kind of view. So it should be also considered still using the third-person perspective depending on the user, and leaving open to switch between perspectives. And also for the gaze cues, they were often not noticed. Like participants focused so much on the task and like what the instructor did, and also the hands, that they were just ignoring the gaze cues. And head gaze even increased mental load compared to no gaze cues, but also the patience compared to eye gaze cues. In general, we noticed that there was a lack of feedback and focus on the task. And the focus on the task reduced the social connectedness, because the participants, as already mentioned, noticed more the task than the instructor themselves. So adding interactiveness through AI could improve this feeling. So that is a potential future work. And with this, I wanted to say thank you for your attention, and I'm really excited for the discussion now. Thank you.
So thank you for the talk. Let's move to questions. In front of it.
Thanks for the talk. And I want to know what's the difference between gaze and head gaze in your work?
So I go back shortly to the slide here. So we have the eye gaze. So it's basically where the eye movements go, and the head gaze is the full head. So with HMDs, often head gaze was used, and it's like a way easier thing to measure. Can you hear me better now? Sorry.
It means it means for the head gaze, the real gaze is synchronized with head motion, right?
You mean the size of
yes.
Yes. We based it on related work, because you also, like, if you made it smaller, you would not know, like everybody that had like a if you ever had like a VR headset on and did something with like measuring gaze, for example, people sometimes look down and like look up with their eyes. So it can be that if you only show where the head gaze or the middle of the head gaze is looking at, that is a completely different point where the interaction is happening. So we showed the whole. Like,
as for the results, what's the difference between these two kinds of measures?
The difference?
The difference of the results by using these two kinds of measures.
The difference of.
Yes, you showed some results, and what's the difference between the comparison of two different results by using two different cases?
You mean what the results are?
Yes.
Yes. So these are the results. So we basically there was not many like there were not many significant results, to be honest. Like, it did not change that much to use gaze cues or not use gaze cues. But at least they changed patience and also had mental load, like an effect.
Okay, thank you.
And also
thank you for
if they would use it or
Next
not.
question.
Yeah, I pass. Okay.
Thank you for your question, by the way.
Thanks for the talk. Doug Bowman from Virginia Tech. So as you were just saying, you didn't find a lot of results with the gaze cues versus none, or the eye versus head. I wonder if that's because the task was kind of purely a motor task that didn't require any like information gathering from the world, and I wonder if you considered another sort of task where maybe you had to look at something in order to understand what you should do with your hands.
Yeah, of course, our like setup is very. The microphone is always dropping. Our setup was, of course, like we only evaluated this in a specific task, and other tasks could lead to different results. We don't like say that it's not like this. We also believe, because we did not use the voice channel or other modalities, that this could also have an influence. So that like gaze, for example, in connection with like talking or like with explaining something, could be helpful, or at least could lead to different results, let's say, because, yeah, so this is, depends on the task probably. That's also what we wrote in our paper. So thank you for your question.
Thanks.
Steve Feiner, Columbia University. I have a question about, you mentioned that there were some people who in the first person perspective felt a little uncomfortable, right? Like someone was standing behind them. What were they told about what was happening? Were they told that their head was essentially going to be roughly where the expert's head was, or they simply just experienced that there were some hands kind of in front of them?
Yeah, we did afterwards interviews, and like I think 3 or 4 at least said that it's, I'm not sure again about the percentage, but like a handful of people said that they felt really uncomfortable when we asked them about like the gaze, or like about the, like the perspective, and also the instructor themselves. So yeah, that was like one of the main findings, because in the long run it could lead to like also problems, right? Even if it's like now productive, if people feel like that it's like uncomfortable, it can on the long run have like negative impacts. So this is also something that needs to be studied a little bit more in the future.
This is a somewhat different question. I wanted to know, before they actually performed from first person perspective, were they told that they were going to be in first person perspective rather than simply seeing hands where the expert's hands would be and not knowing whether the expert was behind them, you know, they're in the same place? What were they told?
So at the beginning, they only, like we tried to be as neutral as possible from the beginning on, so we did not try to prime the participants before that. That was also because some participants mentioned that first they did not thought that much about the hands, but after they saw the instructor in the third person perspective, they did the connection and were like, after that it felt very uncomfortable, because they noticed, oh, this is the instructor currently showing me, and now I have the feeling that this person is behind me. And it even got worse over time.
I see. So the reporting may even differ between which condition they got first.
Yes,
right.
Or at least like we counterbalanced all the conditions, so that we would not have like that much of an influence with all these kind of things, with the Latin square. But yeah, this is we also wrote that in our paper, that is like definitely had an influence on the perception, because if people maybe only saw the hands, could be different. So this is also something that needs to be explored a little bit more in the future.
Okay. Thank you.
So this is the last question, please.
Hi, Matt Gottsacker from the University of Central Florida. I have a question maybe related to that one. I found it pretty interesting that the social connectedness was higher for the first person perspective, because you just see their hands, right? And you don't see the person. So do you know why this happened? Was it like, did people feel like they had a very shared experience or something? Or how do you square that with the unnatural feeling?
So we use the IOS scale, if you're familiar with that. It's like the one with the circles. So either the circles are far apart or like very close together, so intertwined. So it's also like saying that like it's the feeling towards the other person. But yeah, probably because they were in this, like there's also related work that shows that if you see, for example, an VR view of another person from their perspective, you also have more like empathy towards this person and so on. So they also used it to resolve conflicts in psychology, for example. So this could be a potential reason why they also had the feeling, okay, I'm more connected to this person now. Also maybe the connection between them being themselves and also the other person, because the embodiment was also higher. So this could also be that, of course, because it was a unknown person, right? Like we just had this one character, and it was asked if, like, we tried to make it look as real as possible, but was still an artificial character, so nobody could know this person. And so in this kind of perspective, they probably had the feeling that it was also more themselves, so they are also more connected to themselves, so probably this.
Cool, thank you.
Oh, thank you very much. Upload.
Today I'm presenting our paper titled Don't Miss Notifications, Exploring Gaze Notifications for Virtual Reality Cooking Environment. During the interactions in VR, we often shift our attention if we are dealing with multitasking, and so that we may miss important updates or notifications. There is an extensive research on notifications for 2D screens, but in 2D, notifications pop up on a fixed corner of a screen, and you will almost certainly see them. But in VR or 3D environments, information is spread across the entire environment, so notifications can appear in areas outside of our attention. So that makes designing effective notifications in 3D environments much harder. They may be distractive if it's constantly in users' field of view, or may go unnoticed if they are not on the field of view. So prior work investigated world-fixed notifications, where the notifications are static and attached to the certain location in the 3D environment. Another one is the heads-up placement for notification, which are attached to the headset, which means like user is constantly seeing the notifications in their field of view until they dismiss them. Here is a trade-off. World-fixed ones provides better usability, but resulted higher missed notification counts. For the other hand, headset-placed notifications offer higher noticeability, but they reduce the usability. So, how can we design a notification that's in users' field of view and not distracting to the users? Because to keep the noticeability higher, we should show the notifications in their field of view without distracting them. As gaze provides more accurate and immediate indicator of user attention, we want to investigate gaze-based notifications. As our aim is only to investigate effect of gaze, we only included visual notifications in our study. Previous work used gaze as an input, and they found that it increased eye strain, and participants found it not usable. However, we proposed to use gaze as a special anchor, not as an input method, to dynamically position the notifications. So we have two hypotheses. First one is to investigate how gaze-based notifications improve performance and noticeability. And the second one is investigate in terms of the usability. To investigate them, we implemented VR-based cooking environment. The AR version is an open source called ARtisan Bistro. We have 3 stations in the environment, which are burger, pizza, and coffee. Our task requires users to shift their attention constantly as they have to cook burger, pizza, or prepare a coffee. And in our task, 3 customers arrive at the same time and all have 2 minutes lifespans. And participants had to prepare 3 things in 2 minutes. For instance, while pizza is cooking, they have to switch to the burger task, and during the burger preparation, the pizza may be burned. So we chose this environment as users should be aware of all the things going on in the environment. So we propose to use two gaze-based notifications. One of them is the gaze cue. Gaze cue appears at user's gaze position and it automatically disappears after 3 seconds. For the gaze dog, it appears both at user's gaze position and on a fixed place called dog. But in this time, users have to manually dismiss the notification with clicking on them. So one of them just disappears, and other is user have to click on the notification. And we implemented previous world fixed notifications on object and on dock. In on object, notifications are attached to the related of the object, and in on dock, it's very similar what we have in our smartphones. The notifications are stuck on a certain place. We compared 4 notification types, and we had 16 participants. And we measured performance, noticeability, and user experience. For serving time, it shows how long does it take for the participants to serve each customer, and for the number of customers served, how many customers they can serve on the time. And for the noticeability, we ask users to click on the notifications as soon as they notice the notification, except the gaze cue because it automatically disappears. And for the notification clicks, it's how many times they can notice the notification. Our results show that serving time faster with gaze cue compared to on object and on dock, and participants served more customers with gaze cue and gaze plus dock compared to on object and on dock. And for the noticeability, participants reacted faster with gaze plus dock as we expected compared to on object and on dock, and they noticed more notifications with gaze plus dock. Here we don't have gaze cue. As I said, it's disappear automatically. For the subjective feedback, only gaze cue achieved higher scores than on object and on dock, and participants highly preferred the gaze cue compared to other 3 evaluated methods. We believe this is because seeing the visual notifications constantly in your field of view reduces the usability, as we observe with the gaze plus dock. And for the NASA TLX, you can check the paper for the details, but overall, gaze cue received the lower workload scores. And for the presence questionnaire, gaze cue also received higher perceived presence scores. So we say if the time is important in the task, users need notifications in their field of view. Building on this, our findings highlight that while gaze-based notifications are effective, the duration of their visibility must be carefully designed, because if the duration is extended duration for the display times without appropriate dismissal mechanism may increase cognitive load, as we observed in gaze plus dock. And I think I talked about this. we say, like, if the time is important, gaze-based notifications can be more effective. In conclusion, we show that using gaze as a special anchor can make notifications in VR more intuitive and effective. But one key factor we found is the duration of the notification. I mean, like, how long the notification stays visible. Like, if it's too short, users might miss it. If it's too long, it becomes distractive. In our study, we used 3-second duration, which was chosen based on our pilot studies. And the participants reported that this was long enough to notice, but short enough not to interrupt their workflow. Also, this duration is not fixed duration. It should be adapted based on the task needs. For example, fast-paced task may need shorter notification, while the slower task might allow longer visibility. We also found that combining multiple visual feedback, such as showing in front of the gaze position and also fixed position, may reduce the usability. So maybe future work could explore combining with other modalities such as haptics and audio. And thank you for the listening.
So thank you for your talk. Any question, please? Yes.
Thank you for your talk, Pavel Manach of Lancaster University. I'm not sure that I caught it from your presentation, but as I understood from the very beginning, the goal was to basically make the notification less distracting but efficient, right? And what I wanted to ask specifically about the gaze-based condition is how exactly was it placed relative to the gaze ray? Because I know there is a previous work which basically puts information a little bit offset of the gaze ray, so that basically it follows the gaze, but then it does not occlude the information that the person is looking at, and then the saccade onto the information would fixate it within head reference frame. So did you implement it in this way, or was it aligned exactly with the line of sight?
It was following the gaze position, but as you can see in our implementation, like I explained this in the paper more, but if the user is looking down to the table, the gaze position can go under the table. So we added some kind of colliders to there to make it like if its gaze ray collides with the table, for example, the notification should appear a bit above the table. So
got it.
but it follows the gaze position directly.
So the center, right? The ray itself. At
the
what depth? Was the depth somehow controlled?
The depth?
How far? Sorry, how far from the gaze origin?
10 units in unity measurement, like
10 meters.
10 meters. I'm not sure, like this far. Yeah, it was 10 or 8.
Thank you so much.
I don't remember exactly. Thank you.
Thank you. Let's take one last brief question.
Okay, thanks for the talk. Yang from Aarhus University, and I'm curious about the scope of the paper. So what is the reason or motivation for you to choose VR cooking instead of AR cooking? Because in my understanding, in VR, the task is more because of lack of haptic feedback. So your gaze is kind of more occupied by the task itself. And if
you mean why we chose VR over AR, right?
Yeah, because I think
it's because our aim is to investigate the only gaze. So in AR environment, it may be distractive, and maybe results can be different. So we want to eliminate the real world completely. That's why we implemented in VR again.
Okay, thank you.
All right, so thank you for your presentation again.